Okay, so today, as you can see by the spreadsheet here, we're going to be talking about assignment 2. And assignment 1 is due tonight at 11:59 p.m. Just be sure to submit that on time on D2L if you don't want any marks to be lost. Assignment 2 is going to be, I would say by far, maybe not by far, but definitely the most raw programming of any assignment in the class. That's why it's worth the most. And so if you weren't sick of grids from assignment 1, you're definitely going to be sick of grids after assignment 2. The algorithmic part of assignment 2 is not the trickiest part. There's just a whole bunch of stuff to do. So we will have 19 days to do assignment 2, but do not leave it until the last couple of days. It will be very obvious to me when you come to me like with 2 days left and you're just starting the assignment, and my sympathy for you will be much less if that's the case. Hopefully you're not doing a lot of courses and you can start this one early. And just like assignment 1, it will be released at some point this evening, and I'll post on Discord or D2L when that's available. So if you wake up tomorrow, you click the link, it'll be there. So just like every other assignment, I'll start off with a demo of what we have to do, and then I have a bunch of slides for this one. So I'm explaining everything in great detail. So here's the, let me just full screen this actually, make it a bit easier to see. Okay. So the environment is exactly the same as last time. So you are now aware, because of assignment 1, what this environment is and how it works. The major difference is that we are doing, instead of BFS and DFS, there is A star is the algorithm that we're doing. So from this drop-down menu, you can see, okay, we have the student A star, which is the same dummy path that I gave you for assignment 1, so you'll just eliminate that. And then if you go to solution A star, you will see that this actually computes the shortest path using A star. And then similarly, there will be tests you can run. You can switch environments, all sorts of different things. The major change since the last assignment is I have included this updated user interface. So for example, when I'm doing the animated search, and I have this now, you can see the parent pointers here. So you can see as the search is going on, it will show, okay, the last node that we chose for expansion, it will show the path to that. So let me show this again, maybe over here. Yeah, so you'll be able to see the last node that you selected for expansion. The UI will draw the path to that last node that you selected for expansion. And that's just a little bit of extra debugging help for you. And also, you can toggle on or off the drawing of the open and the closed list if you want to. So you can have both, neither, or either one. That's up to you. And if you don't want that parent drawing thing, you can just turn that off if you want to as well. So that's the only real difference with the user interface. Other than, now we can select from having 8 actions be legal or 4 actions be legal. We can select our heuristic function that we're going to be using, and I'll go into that more on the slides. And also, there are now different sizes of the object as well. So for example, this is the standard 1-sized object, so it's just a 1, it occupies 1 cell in the grid. This is a 2x2 object, and this is a 3x3 object. And you can see that because the object can be different sizes, the optimal path even from the same start and goal to the same goal location may not be the same optimal path for objects of different sizes. So the easiest possible example of this is if I go from right here to right here. Well, I'm of size 1, so I can go through this little maze. But if I change it to size 2, now I would have to go up and over that bridge and around because that's the only legal path. Okay? And if I go to size 3, then that is no longer a legal path because I can't fit over here, but it would be legal to do something like this. So those are the major differences. However, there's also this ominous button right here that says unidirectional, and when you select it, it goes to bidirectional. And so I'll get to this at the end of the lecture, but sort of the extra thing that you have to do in the grad version of this course is what's called a bidirectional search. And if I go to the animated search here, you are actually searching from the start and the goal at the same time. And then the path is found when the 2 closed lists meet. Okay, so that's the little 20% that the grad students have to do that 3200 doesn't do. But without getting ahead of myself, let me go into the actual lecture slides, because that's where the bulk of the material is. And then after that, of course, I'll look at the code once you know what's going on. Oh, sorry, there's one more thing for the user interface that I did not show, and that is when you hold the right mouse button, you will show, and let me go to the solution A star, you will show in pink all of the cells that are connected to that cell. So connected meaning that there's a path possible to it. So for example, if I right-click right here, it's possible to get from this cell to all of these cells, right? It's possible to get from this cell to all of these cells. If I change the size, the connectedness changes. So you can see here that, for example, there's like a one thickness right here where it doesn't come up as purple. And that's because the pink square that's being highlighted is the top left of the object, no matter how big the size is. So if you have an object of size 3 by 3, it can't get within 2 of the coastline because it's not legal to fit it there because it would be overlapping 2 different colors. So that's the only thing that I've left out so far. And you will have to be computing this connectedness in your assignment, and I'll have slides describing that. But that's the only other thing, and that's via the right mouse button. So I apologize to people with Macs. That may be a little bit annoying to press, and I actually brought in like an actual mouse to connect because I'm not very good at right-clicking on the Mac yet. Okay, so that's the only extra thing. Now we'll get into the slides. So today we're talking about assignment 2. We're talking about a bunch of pathfinding optimizations on grids, and then at the very end we'll talk about bidirectional search. So what's new in assignment 2? We have the A-star algorithm. We have multiple object sizes. You will be doing size 1, 2, and 3. 8-directional movement instead of just 4-directional movement, which introduces its own intricacies. We're talking about heuristic functions. We have these things I'm calling connected sectors. So sectors are just sets of states that are all connected to each other. Some pre-computing and optimization, as well as the bidirectional search. And as I said before, this assignment has by far the most like just raw coding in it. None of it is too difficult. There's just a lot of it, right? So make sure you get started on it early. And there's the A-star graph search algorithm. You've all seen this enough by now. And what you're going to do is the exact same thing you did in assignment 1, except instead of BFS, where you would take the first node, now you're looking at the open list and finding the minimum F value. And then that's it. That's A-star. You've already got that kind of implemented. You just need to find the minimum F value. So the majority of the work in this assignment come from the things that are not the A-star search algorithm. And so here's some pseudocode for you for assignment 2 for A-star. There you go. That's it. That's the A-star part. But you don't need to worry about that too much. It's just there. I'm not going to go over it. It's just, this pseudocode in JavaScript algorithmic form. Now this may not be copy and pastable and just work, but I wanted to give you a good starting point. The node class is going to be modified. So before we just had the XY state position in the node as well as the action and the parent, but now we are also storing the G cost, the H cost, and actually I'm also storing the F cost. So F is just G plus H. I don't have that there, but trust me, it's in the class, and you'll see that when you get it. And this note down here is to calculate the child's G cost. That's just the parent's G cost plus the cost of the action to get you, right? So how much it cost me to get here is equal to how much it cost me to get here from my neighbor plus the cost to get to the neighbor. So that's a really easy calculation. Now, just like before, we have the same environment with the same XY states. Starting in the top left at 0, 0 and going down to xy minus 1 in the bottom right. However, now we have 8 actions instead of just 4 actions. And so we have diagonal actions, which are like -1, -1, 1, -1, -1, 1, and 1, 1. So those are the diagonal actions. And with those diagonal actions, because yes, you do move a little bit further, we have new costs associated with those actions. So no longer can you just say that the cost is equal to the path length times some number, like in assignment 1, because they were all costs were 100, but now you have diagonal costs with their own cost. And I actually have a little bit of code there to show you how to get that cost. Legal actions. This is going to be changed for this assignment. So a legal action for assignment 2. First, the object can only occupy a region if all tiles underneath are the same color. So this was not a problem in assignment 1, because of course for an object of size 1, it can only occupy a single tile. But for example, an object of size 3 by 3 occupies 9 different tiles. And so it's only legal to put it there if, the first thing, if it can actually be put there, right? And meaning all the tiles underneath are the same color. An object can only move to a space if all of the new region is also the same color as all of the old region, right? So if you've got an object of size 3 and it moves like to the right, you're going to have to check 3 new spaces, right? Not just 1 new space. An object must be entirely within the map. And so this was not really an issue for assignment 1. It just had, the one tile had to be within the map. But now, for example, you can't have a 3 by 3 object in the very bottom right corner of the map because it would overflow the edge of the map. And this is the most important. A diagonal move cannot allow the object to jump over a tile of another color. And I have a illustrated example of what I mean by this in a second. So object sizes, what do I mean by that? Well, let's say we have an object that's right here. An object of size 1, the XY location is obviously just that location, right? And it only occupies that tile. An object of size 2 and an object of size 3, the X there, that is the XY location of the object. So that is the top left position of the object. It's not the middle, it's not the bottom right, it's always the top left. And so if you want to get the bounds, for example, of a 3 by 3 object, well, it would be from this up to this plus 2 and down 2. Okay? So that's what the object looks like. An object of size 3 can fit right here because all of the tiles underneath are all blue, or they all have the same integer value from our environment. And an object of size 3 cannot fit right here because it would be overlapping 2 different colors. So that's the example right there. Legal actions. So let's say that we have a state right here. Let's look at our legal actions now. So let's look at the 4 direction actions. So up, down, left, and right. Those are the same from assignment 1. So we can move up, we can move down. We cannot move left because it's a different color. We cannot move right. Or sorry, we can move right because it's the same color. However, the diagonal actions, I'll do the true ones first. So we can move up and to the right because it's the same color. We can move down and to the right because it's the same color. We cannot move down and to the left because it's a different color. But oh look, this is the tricky case here. We cannot move up and to the left. And the reason is, if we treat this square as like a physical sheet of paper, right? Imagine this is a physical thing, and we want to slide it from right here to right here. So if we slit it, this is sort of what the corners look like, right, as we're sliding that up. And I'm saying if that sliding action makes it go over any other different colors, then it's not a legal action. Okay? So that's the way to look at that. If this, by sliding it diagonally, if it would touch any other colors, that's not legal. So the way I phrase that is that an object, no part of an object can jump over any other colors with a diagonal move. So let's look at a 2 by 2 example. Here, I cannot move up because this tile would then be overlapping this tile, right? It would be a different color. I can move to the left. I cannot move right because similarly this one would go over to the right and it would overlap this. I can move down. I cannot move up left because this tile right here would be sliding over this green tile. I can move down and to the left because there's nothing stopping that. I cannot move down and to the right because this tile would be sliding over this tile, this green one, and I obviously can't move up and to the right because multiple tiles would be overlapping with different colors. Okay, so those are legal actions. Now, sometimes this can be a little unintuitive, but for example, if I wanted to go from this starting location to this goal location, I cannot do these diagonal moves because I would be jumping over tiles of a different color. However, this is still a legal path because I could go all the way around, up and over to get to that tile. Okay? Now, if I have this situation, I actually can go through this path, but I still can't do it via diagonal moves because I would still be jumping over, this tile would be jumping over this one. So I can go through this, though, by going up, then right, then up, then right, then up, then right. Okay, because that would not be sliding over. So just look, this 2x2 object can move up, then it can move right, then it can move up, then right, then up, then right, then up, then up. So I could have a path here, but I cannot have it be with diagonal actions, right? And your legal action function should take care of all this. Here is an interesting legal action fact. And it is partially why I like this rule of no jumping over things. And you may say, oh dear, there's a lot going on here, right? I'm going to have to be calculating a whole bunch of stuff. These rules seem a little bit complicated. But luckily, this rule makes it all pretty simple. So here we have an object at a given state. And we're looking at only the diagonal actions here. Okay? So I can move up to the right. I can move down and to the right. I cannot move down and to the left. I can't move up and to the left. Now, let me just put down the cardinal action legality as well, which is much easier to calculate, right? So let me put that down. Who can notice something about the relationship between these two? Yeah?
If you can't move in one of the four directions, but to the left, then the two diagonal, next to it, you can't move there either.
Yeah, so it's a little bit hard to explain, but I think you got the idea here, which is that a diagonal action, for example, move up and right, is only legal if both moving up then right and right then up are also legal. Okay? So the diagonal is only legal if both the cardinal ways of getting there are also legal. And so you can calculate the cardinal action legality, and then you can use that to calculate your diagonal action legality. And that maintains for all object sizes as well. Here, for example, you might say, why is down left not legal? Because left then down is not legal. So that's why we can't do that. Down then left is legal, but left then down is not legal. If we look back at this example, the reason moving upright diagonally is not legal is because moving right then up is not legal. However, up then right is legal. All right, so that's a really interesting fact that you can use to help optimize that calculation. Next, we have paths. So at first glance, you may say that this is the shortest path between these 2 points, but it is not. And the reason it's not is because these diagonal actions here are not legal because they're jumping over things. So when you take these diagonal actions around corners, you kind of have to meet them at the corners of those. So you still have a diagonal action here. Excuse me. However, you cannot move to this one with that diagonal action because you'd be jumping over a tile. So this would be the shortest possible path. And the length of that path would be, well, all of the cardinal actions, 102, 3, 4, 5, 6, plus 141, which is that cardinal action, and then up 2 more to make it 941. So you would add together the individual costs of all of those. Next, we have heuristic functions. So this is our guess at how much distance that we have remaining. We've covered these in depth in a previous lecture. We will be doing this in assignment 2 via the estimate cost function. So estimate cost, that is our estimate of the cost of going from one state to another state, and this will encapsulate our heuristic function. We're going to have 4 different heuristics for this assignment, and these will just be stored in the config as strings. So just like assignment 1, where it was like, if the config.strategy is equal to this, here we'll have this dot, I can't remember what the actual variable is called. We'll get to that in a bit. But they will have these 4 strings. So if it's just dist, then you will calculate the Euclidean 2D distance formula. That's pretty easy. If it's card, it will be the cardinal Manhattan distance. If it's diag, it is the diagonal Manhattan distance. And if it's 0, you literally just return 0. I think it's already done for you. I think all of them by default return 0, and so this one doesn't even need to be modified. So again, in visual terms, if we have a current xy and a goal xy, then this is the Euclidean distance. That's literally just Pythagoras, square root of whatever. Here we have the Manhattan distance. This is really easy. You just take the absolute value of the difference in x's and y's and add those together. The diagonal Manhattan distance, obviously, you don't need to worry about obstacles, right? So you may say, oh, this isn't a legal path, but the heuristics don't care about legal paths, right? You're taking the shortest possible path considering there were no obstacles in the way. And the way you calculate this one, it may seem a little bit tricky at first, but essentially the pseudocode for this one is calculate the y distance between the 2 points, then calculate the x distance between the 2 points. Whichever of those is less, that's how many diagonal movements there are. And then you take the other one and subtract that, and then that's how many cardinal directions there are. Okay, so that's a little bit of a shortcut on how to calculate that. So here you can see that our y distance is 1, 2, 3, 4, and that's less than the 1, 2, 3, 4, 5, 6, 11 x distance. And so we have 1, 2, 3, 4 diagonal movements, and then 7 cardinal movements. And so that's how we calculate that. And then the 0 heuristic, well, it's just a 0. Don't need to draw anything, right? Okay. Next, we get to one of the most annoying parts of the assignment where you're going to do a lot more BFS to calculate something. And this is what I call the connected states. And so anything to do with connectivity, connected sectors, sector numbers, all that kind of stuff is stuff that I came up with. You probably won't be able to Google how to calculate connected sectors. A, I'll be disappointed if you do because I think my slides are good enough. But B, just to let you know that, I don't know if anyone else calls it that. That's just what I call it for this assignment. So states are going to be considered connected for an object of a given size if any legal path exists between them, no matter how long that path is. Okay? So if you can get from one to the other legally at that size, then they are connected. A connected sector is the entire set of states that are all connected to each other. And so in assignment 2, holding the right mouse button highlights all states that are connected to the clicked state. And you may think to yourself, well, that seems like it's going to be an expensive computation, because in order to see which states are connected to this, we may have to actually compute all the possible paths to this thing, but it turns out that's not the case, luckily. We can do a little clever trick. And also something that's nice to know and is usable for a little optimization later is that connectivity is transitive, right? So if A is connected to B and B is connected to C, that must mean that A is connected to C. Okay? It doesn't mean that the shortest path from A to C is through B. It just means that if one's connected to another, which is connected to another, the first and last ones are also connected. So let's just have a look at exactly what I mean by connectivity. So these two are connected, right? For size 1. That's an important thing. These are all connected for size 1. So A, B, and C, I can get from A to B. Yep. I can get from B to C. Yep. Therefore, I can get from A to C. But look, I don't need to go all the way down here to B to get to C. It just means that if I know A and B are connected and B or C are connected, then a path exists between A and C as well. However, these are not connected for size 2 or 3. So who can tell me why these are not connected for size 2 or 3? Hand up. Don't just yell it out. Someone different. Yep.
Because if this throughout the size, if you see that from the C part, it will go to the green part.
Exactly. Right? So if you can't fit it there, you can't pathfind there. So that's why they're not connected. However, also, even if you could fit it there for size 3, there would be no legal path from B to C with size 3, or from A to B, for that matter. These are connected for size 2. Okay, so I can get from A to C with size 2, and I can get from A to B with size 2. And that means I can also get from B to C with size 2. Those are connected for size 2, but they are not connected for size 3. Yes, I can fit objects of size 3 at all those locations, but I cannot move them to the other locations, so they are not connected. Also, The trivial case, these are obviously not connected because no path is going to exist between two states with different colors. Okay, so they're sad. So this is a connected sector for size 1, meaning that anything there that is pink can reach anything else there that is pink. Okay? So when you right-click somewhere on the map, anywhere there can path, or they'll all show up pink. If I clicked on the blue, all the blue ones would show up pink, etc. I don't know why I have that slide there. Okay, so computing connectivity. How do we do this magical connectivity computations? Tongue twister. So first, we notice that a diagonal move is only legal if both surrounding cardinal actions are also legal. Okay, why does that help us? Because it means that a path with diagonal moves only exists if a different path with only cardinal moves also exists. Okay? So that means that cardinal connectivity is the same as diagonal connectivity. Meaning that we cannot have a path that moves with diagonals unless we also have a path that moves without diagonals. Okay? So, okay, all we need to do now to compute connectivity is use breadth first search with 4 directions. And we've already done that in assignment 1. But are we going to have to compute this one to this one, and then this one to this one, and then this one to this one, and then this one to this one? At first it may seem that way, but let me show you a visual example of this sort of good amortized time complexity way of computing this connectivity. So I'm going to explain the algorithm intuitively and visually first, and then I'll give you the pseudocode for the algorithm later. So we're going to start up in the top left corner. And what we're going to do is we're going to have a function that we run, and then after that is run, we're going to go to the next tile, and we're going to run the function there. Then we're going to go to the next tile, and we're going to run the function there. And we do this for every tile in the environment. Here's what that function is. We're going to look at this value. This is set up to be all zeros initially. And these zeros, these numbers, are what I'm calling the sector numbers. So everything initially at the start has a sector number of 0. Okay? Now, I'm going to look at a particular spot, and if it is 0, it means I have not computed the connectivity for that point yet. So I'm going to start my algorithm right there. And what am I going to do? Well, if I find a 0, and my object can also fit there, so for size 1, it can fit everywhere, I'm going to increase the number by 1 and put it there, and then do a BFS outwards from this, setting every legal action I touch to the same number. So I've set this to 1, then I do BFS outward, setting those to 1, then those to 1, all of that until everything that I can touch is set to that same number 1. Okay? And what I've done there is I've shown, oh look, everything with a 1 is connected to each other. So I've computed all of that connectivity in a single BFS. Now, I said that the algorithm then goes to the next spot. But if that number is not 0, I've already connected its connectivity, or computed its connectivity. So I can keep skipping until I get to the next 0. Okay, now I'm at 0. I increase the number by 1, I put it there, and I breadth first search out from there until I've hit all the legal actions. Okay? Now I keep going, and I'm going to hit this one in the middle at some point, fill all of those out, then I keep going, and I hit this one at some point, and fill all of those out, and then it goes, and I'm done. So, basically all we've done is the running time of this algorithm is the size of the grid times 2, essentially, because we had to iterate to check every one first, and then when we find a place that's not done yet, we have to BFS out from there. And if we think about it, the most we will inspect every one of those tiles is approximately twice, but of course we also have to check with the legal actions, etc. So here, when you're also doing your BFS, you can use the sector numbers as the closed list. This is a little optimization on this. You don't need a separate closed list because you're setting things you've already touched to 1. So if the number's not 0, it's already been computed. So you can just skip that, right? So when I BFS out from here, for example, let me just go back upwards. So if I'm at this particular case, let's say I'm doing the children of this one. When I generate the left child, well, that's already a 1. I don't need to compute it again. So I would not add that to my open list in that BFS, right? So this is a bit of an extra optimization that you can do when you do these BFS. And I'm going to call that the Cardinal BFS when you run it. So here is that function in pseudocode. So in your assignment, you're going to have a function which is called compute sectors. And when your search student class, when the constructor is called, which is usually done when you change parameters like the map or whatever on the starting page, this function is going to be called inside the constructor of your class. So first what I do is say, okay, I'm going to set up a 2D array, which is this grid. This grid is essentially just a wrapper around a 2D array in JavaScript. It's going to have the size of the map width, and map height, and it's going to be given all zeros initially. So this is pseudocode, of course, so that's my way of saying this is a 2D array initialized to zeros, the same size as the map. Now I'm going to set my sector number. This is the value that I'm going to be inserting into that map as I BFS around to 0. And then I say, okay, now I'm going to have 2 loops, one over the x's and one over the y's. So this will touch every square on the map, and this is the outer loop of that computation. Then I have to check if the sector number is not 0, or I can't fit a thing of a given size at that location, then continue. So what that means is, let's say I'm doing size 3 now with this compute sectors. This is supposed to be discard. So if we look up here, there's an S here. So this is supposed to be oh, please don't tell me I have another slide where I do that. No, I don't. Okay. So this is supposed to be for s equals 0 or s equal 1, s is less than max size, which is 3, s++. Okay. I don't know why I didn't have that in there, but I didn't. Okay. So for each size that we have, for each width, and for each height, we're going to do this computation. And if sectors x, y, and of course that'll also be s in there, is not equal to 0, or we can't fit, then we skip this one. Otherwise, we can start a new BFS there. And if we can start a new BFS there, then we increase that sector number by 1. So now we'd be putting the number 1 in there. And we do a cardinal BFS starting at x and y with the sector number that we want to fill in. Okay? And that's it. And then we'll have a function is connected later, which takes in an x1, a y1, x2, and y2, and we'll call that function to see if those two locations are connected. And we may also pass in a size parameter to that to say, are they connected of a given size? And that's it. That's the whole algorithm. You just have to write that cardinal BFS. But you know how to write BFS by now, so I don't need to go over that. And all we need to do to see if two things are connected is check to see if their sector numbers are the same. That's it. So now we know if a path is possible with a constant time lookup into a 2D array. And so maybe the first thing you do in your algorithm is say, hey, if they're not connected, don't do any search at all. Right? So that's a really cool speed up that you can do. Connectivity checking. So two tiles are connected if their pre-computed sector number is the same. Look at that. That's pretty cool. We can use this as a pre-check to see if a path is possible before actually trying to compute it. And if the start and goal are not connected, then no path can exist between them. And so let's look at bigger object sizes. So, of course, with size 2 and 3, this gets a little bit more complicated. But essentially, this one is connected to this one. Right? So these two states are connected for size 3, but it is not connected to this one because I can't fit it there. So here are all the places in this environment where I can even fit an object of size 3, right? All of those x's, they're where I can legally fit objects of size 3. And if I do this same thing for size 3, it's the exact same algorithm. It's just that whether or not I can fit somewhere, and the legal actions may be a little bit different. So here's what I get at the end. That is the sector map, or the computed sectors for an object of size 3. And the really cool thing is you can see there's still a bunch of zeros. So what does a 0 mean here? It means you can't fit the object. So later on, if you need to know if you can fit an object somewhere, you can use the connected sector number, and if that's 0, that's a constant time lookup of that. So you no longer need to say, okay, do I need to check all 9 places and see if they're all the same? You can just look up the computed sector map and say, if it's a 0, I can't put it there. I'm sure of that. So your search student object will not reconstruct if a different size is selected in the UI. So changing the size in the UI does not reconstruct your object. So that means you must compute connectivity for all sizes, for size 1, 2, and 3 in that same function. And so what I recommend is you have a this.sectors, a 3-dimensional array. Okay? And if 3D arrays are hard to visualize for you, just picture it as a 2D array that holds arrays. Right? That's essentially what it is. And so this means that sectors x, y, s is the sector number for state xy at size s. So you can have a 3D array, or another way of looking at it is just a 2D array of arrays. In practice, what I actually do is use 4 elements in this array. I go to max size plus 1, so that when I check my array xy size, then I can just say, okay, the 1th element, which is actually the 2nd element, is my size 1, right? So indexing this by size 1, I get the size 1 thing. Otherwise, if you don't have this, then you might have to say, okay, if I have 3 sizes, 1, 2, and 3, and I want to store those in my this.sectors, well, I'll have to store those at 0, 1, and 2. So whenever I index my size, I actually have to say size minus 1, right? So that's just a little workaround you can do. If you don't want to have to say size minus 1, you can just stick a little dummy element in there to get that. Now, we're going to talk about speed optimizations, because that's basically all you have to do for the assignment. Now, I say all you have to do, but that's easier said than done. But here is how you make it fast. So the following optimizations will not necessarily affect the number of nodes generated, meaning like it won't affect the big O running time of any of these algorithms, but it may dramatically speed up the actual running time, which is what we're concerned about for the assignment. None of these optimizations are required for getting full marks, except all of your tests do have to run in under a second. Okay, so per test. So some of them may be required. If you're like dragging your path around and you want it to be super smooth, you're probably going to have to implement some of these optimizations. Here's the first one. This is the connected sector optimization. So for larger object sizes, we may have some tiles that have a 0 value. And what I just said is that this means that the object cannot fit there. So by pre-computing these values, we can use them later instead of doing the full object size check to see if all the underlying tiles have the same color. So let's just have one more look at this. If I see any tile here, for example, this might be my map for size 3. If I see a 0, I know that this 3x3 block does not contain objects of the same color, or it does not fit on the map. So that's one function that we can write really, really easily, canFit, which just looks up the sector number. Here's the next optimization. The rule of no jumping over diagonals actually gives us an interesting property, and I talked about this already, but I have it listed here specifically as an optimization. So a diagonal xy is only legal if both x then y and y then x are then legal, and this holds for all object sizes. So I already went over these examples. I don't need to say them again. So we can use that fact to help optimize our isLegalAction function. So the most commonly called function in A2 is probably isLegalAction, because whenever we generate children, we have to look at all 8 legal actions, which is 8 things that we have to check. And we can use the pre-computed connectivity sectors to check for legal cardinal actions, since actions are only legal if the source and destination tiles are connected, right? So no longer do I have to do this special check for whether or not something is legal, because if it was legal to go from here to here, that means they're connected. So I can just check their connectedness, which I've already computed. But let's have a look at this and how we may be able to optimize it. So let's say I'm trying to see if the action AD is legal. So going from here down right to here. So this diagonal action AD is only legal if AB, if that's legal, BD is legal, AC is legal, and CD is legal. Okay. AB is legal if A and B are connected, right? AB, that means that AB, BD, AC, and CD are legal if each of A, B, C, and D are all connected. So, if A, B, C, and D are all connected, then AD is legal. So that's 4 checks in the connectivity grid. However, because connectivity is transitive, if A, B, and BD are connected, that means AD is connected as well. So all you really need to check is if AB, AC, and AD are connected, then AD is legal. So to check if a diagonal action is legal, all you need to do are check three numbers in the computed sector grid, okay, which is a lot less expensive than having to go through all the actions and check, okay, are all of my colors the same as all of the colors in the next one, and have I not jumped over any of these tiles? Like, that would be crazy if you had to do that every single tile. That would be like 50 computations, and we've reduced that to 3. Okay, so this makes things super fast. Here's another legal action optimization, if you want. And this, believe it or not, I did this in C++, and it did not speed things up. The reason it did not speed things up was because additions were so fast that looking this up in the array took longer than just doing the additions in the first place. So this optimization is a theoretical optimization that sometimes leads to faster code, sometimes doesn't lead to faster code, depending on how things are stored in memory, etc. But if you get everything working and you've got your 100% lined up and you just want to be the fastest in the class to get the street cred, then have a look at that, implement it, and see if it's actually faster or not. But here's what it is. Our environment is static. Our legal actions will never change, right? Tiles that have the same legal actions for a given object size, they'll have the same legal actions every time you visit them. So if we keep checking them, why do we keep checking them, right? So you can pre-compute all of the legal actions for all tiles, and then later just iterate over the list of legal actions rather than iterating over the list of all actions and checking if they're legal. So, you know, the average legality of a tile might only be 3 or 4, but every single time we go there, we're generating all 4 and then checking if they're legal. But here we could pre-compute for every action in the environment all the legal actions, store them in a 3D array somewhere, and then when we go to that state to generate the children, we just iterate over the legal actions. We don't have to check anything because we know they'll still be legal. And this will result, I should say, could result in a bunch of time saved. And here's what this looks like. In the end, you get a big array, another 2D array of arrays, where in this tile, I'm computing the legal actions for that tile. So what are the legal actions for this tile? Just moving down. That's it. So when I go to compute the children of that tile, I know what the legal actions are already. Here I have 1, 2, 3, 4 legal actions. So I've pre-computed those once and then just saved them. Okay? Now you could even go further if you want to and say, why do I even need the actions? Why don't I just pre-compute the states that I'll end up in from this state? But it turns out you actually do need the actions because the action costs are associated with the path, right? So I would stop probably here rather than going to that next step. Another optimization. We have talked about this already, but I have it in here just for completeness. The closed list stores unique states. Each state on the map will either be in the closed list or not in the closed list. So you could store a Boolean 2D array for your entire environment to represent the closed list. As I said, we've already talked about that. This makes everything a constant time lookup. Okay, open list optimization. What I recommend, just to get the assignment working, is at the very first thing you do is have an open list, which is just an array, okay? And then to get the minimum thing from the array, just write a function which looks over the array, looks at all the f values, and returns the minimum one. Once you have that working, I've included a binary heap data structure, which can act as a priority queue, which will make the minimum element of the binary heap accessible in constant time, okay? So down here, what you do is you would set let open equal new binary heap, and then you have to pass in as an object a sorting function. And in the code, which I will show you, I've showed you an example of how you do that. And then open.push adds a node to that binary heap. Open.pop will return and remove the node. Or open.peek will return the node but not return it. Okay, because for the bidirectional search, you're going to want to look at both open lists, but only actually remove one of them, possibly. So the original data structure did not come with a peek, but I added a peek to the data structure. Okay, here is a BFS optimization that you may or may not have used for assignment 1, but you are free to use for assignment 2. If you actually implement BFS iteratively, like we've been showing, with an actual queue that removes things, that can have reduced performance. Okay? So how can we do better? A vector implemented queue needs to, in an actual vector, I'm not sure exactly what JavaScript is doing. JavaScript is actually remarkably fast with shift, meaning remove the first thing from it. But in an actual vector, you know that if you remove the first thing, everything else needs to be shifted to the left, which is a linear time operation, which is really slow. That can be very slow in practice. And also, it means that as our lists grow bigger, our operations become slower, which we don't want at all. So performing lookup in the closed list, if you do this, can be very, very slow, right? Or taking something from the open list. So let's avoid an actual queue altogether. So we're going to simulate a queue without actually having a queue. So to insert into the queue, we push the state into the back as normal. So adding things to the vector, that's normal. However, instead of actually removing from the front of the queue, what we do is we're going to store a pointer or an index to where this simulated front of the queue is, and just point there rather than actually removing stuff. So I have an illustrated example in a second. And then instead of checking if the queue is empty, you check to see instead that the index that you have is pointing to the end of the queue. So here's what that looks like in practice. So here I've got a queue with one thing in it, right? So I'm going to remove that one thing and then add some successors. That's what we do with our open list. So here's what it looks like after this. So this thing has been removed from the queue, and now our queue contains 3 things. But what I'm saying to do is instead of actually have a vector which we remove something from, keep it in there, right? Keep it in there, and just increase where we were first pointing to the start of this vector. This is the next thing that we will remove from the vector. So after I've added 3 things, now this is the end of the vector. That'll always be the last element. But this is where I'm going to take the next thing from. So the key thing is here, whenever I take something out, instead of actually taking it out and doing that expensive left shift, just move my pointer to the next one. If that's an actual pointer to memory or an index that you store of the array, that's what you can do. Then I'm going to take another thing out and expand that one, and that's what I get. And then as I remove things, this is how I'm going to check to see if it's empty. The vector itself still has a ton of stuff in it, right? But my simulated queue is now empty because the beginning pointer is equal to the ending pointer. So that's a way to speed up your BFSs even more. And obviously, this uses more memory because we're never deleting anything, but the memory is still the same in the worst case. It's just in practice, you'll have to store a little bit more. Another thing which is not necessarily an optimization, but it could be, and it could also lead to jittery behavior in the paths as you're dragging your thing around, and I'll show that in a demo in a second. Tie-breaking F values. Well, many nodes in the open list can contain identical values for F equals G plus H. In fact, many of them often do, especially when there's no obstacles. Every single node in the rectangle between your start and your goal will have the same F value, the exact same F value. So when you're taking the minimum F value, what does that actually mean? So how you tie break these can have different effects on how your path look and can also affect the number of nodes expanded. So consider, how might you tie break this? Well, if you tie break this by doing nothing and just saying, give me the first one, that's one way of doing it. That's what the binary heap will do by default. But what about if we look at G and H? Maybe we want to take, okay, if two F values are tied, would we want to take the minimum G value or the minimum H value, or does it even matter? So let's have a look. Here's what can happen if you take the minimum F value first. You have a start and you have a goal, and the closed list is essentially going to look random in between them, right? It's going to at least expand the minimum path, but we have no guarantees on what it expands because it has no way of tie breaking the F. It just chose whatever the binary heap did to insert those. But look at this. If we tie break on the minimum G value, then this means the next node we're going to expand is the closest one to the start. Do we want to do that? Maybe not, right? Because look at how many nodes it expands. It expands every single node that could be on the optimal path. If instead we tie break on minimum H, then it chooses for expansion the thing that's furthest from the goal. Well, the thing, technically it takes the thing that has the least heuristic, and if it's the least heuristic, it means closest to the goal, right? So the thing that's furthest from the start. And this is what your paths will look like if you have no obstacles. So this is certainly more desirable than this, but whether or not that saves you time in your tests or not, you can fool around with that tie breaking if you want. But oftentimes I get people say, your open list, your closed list visualization looks different than mine. Why is that? It's because of tie breaking. And just for simplicity's sake, I have not included any tie breaking in the solution. So if you see the solution, it's just doing this. It's going to look jittery as you drag it around, and the paths will kind of wiggle. They'll still be optimal paths, but I have not included any tie breaking, just that so you can see what happens if you don't. The next thing, bidirectional search, I'm going to have to speed up here a little bit. So far we've looked at finding a path from the start to the goal. What about the other way around, right? What about both? Bidirectional search starts from the start to the goal and from the goal to the start. And the search stops somehow when the graphs intersect. And so intuitively, we can visualize why this may be desirable over unidirectional search. So search algorithms work outward from a start, creating a radius of expansion. And so which has a larger total area? One circle with diameter d, or two circles with diameter d over 2, right? So look at this. If I have one circle with this huge diameter, or two circles with this diameter, this has a much smaller total area. So in the best possible case, bidirectional search can save us a bunch of expansion. That's what it looks like. This is the area of the circle. That's the number of expanded. And so the sum of the small circles is far less than the one bigger circle. So that's the idea behind bidirectional search. So in a single search, you have one circle with diameter d. And in this case, okay, I gave a numerical example, but this actually doesn't work out as well. I'm going to delete those slides, so ignore that. But the algorithm modifications you need to make, well, you may need to use two open and closed lists. So you'll have two open lists, two closed lists. You're going to add the start node to the starting open list and adding the goal node to the goal open list. So there's a start open list and a goal open list. And now you have to be careful because going from things in the second open list from the goal, you're measuring the heuristic to the start. You're no longer measuring the heuristic to the goal. So you have to be careful of that. So you could possibly use just one open list and one closed list, but don't do this. It's actually kind of a nightmare in practice. In bidirectional search, what is the goal test function? Well, if all you did was test whether or not you've reached the goal or the start, you may have well just done like a unidirectional search, right? And so maybe it's when the closed lists intersect. Maybe it's when the open lists intersect. I recommend, if you are interested in this sort of thing, trying these out. But the actual answer is that when you take a node off of one of the open lists, if it's in the other closed list, it means that you have found a path. Now, will that path be the optimal one? I don't know. So you could do things like, okay, how am I actually going to choose the the node to expand? Well, you're going to have two open lists, so you can check the minimum f value from both, and you can either, say, alternate going back and forth, or what I do in the solution is I look at both and take the minimum f from both. And so there's all sorts of different ways that you can do this, but I say just do the easiest one. What about optimality of bidirectional search? Can we ensure optimality? So for example, if we stop the search completely when we find a node that's in the other closed list, it means yes, okay, we do have two paths that meet. But look at this example. Here, from the start to this purple node, that is the shortest possible path from the start to this node. This is the shortest possible path from the goal to that node. But this is not the shortest possible path from the start to the goal, right? The shortest possible paths from two locations to a common location does not mean that that is the shortest total possible path. So, if we stop at the first solution, it may not be an optimal one. So just because it's A star, optimality of the first solution goes out the window when we talk about bidirectional search. And this is actually quite a complex topic, but it's not going to be worth a ton of marks on the assignment. So for A star, we can be optimal if we want to. So what we're going to do is we're not going to take the first solution we find. We're going to initially set a solution cost to infinity because we haven't found a solution yet. When we find a solution, we set it as the new best solution if we find a new best solution. And what we're going to do is we're going to stop the search when the next node's f cost is greater than the cost of the best solution so far. Why? Because when the two first things meet, it's possible that there's actually still a shorter path between the start and the goal on the open list. And that will only be guaranteed to find that when the f cost of one of the things that we pull off is greater than the best solution that we found so far. Not going to go into the proof of that. I don't have time. In practice, this doesn't save much time over unidirectional search, but it does make it optimal if you do want to be optimal. So I know this is a lot of text, but it just means you don't have to worry very much. What do I want from bidirectional search on your assignment? I want you to use two open and closed lists, one that starts from the start, one that starts from the goal. Add the start to the starting open list, add the goal to the goal open list. Return the contents of both open and closed lists for visualization. So if it's bidirectional search, in get open and get closed, you have to return the contents of both open and closed lists. Okay? The animated search, I should see the open and closed lists growing together. That's the main thing that your marks are going to be based on. I want to see that your search is actually bidirectional. Show a path if one is possible. So if I am clicking on two connected states, it should return a path. That's all I really want to see. It doesn't need to pass the tests, and it doesn't need to be optimal. However, that will get you 98% on the assignment. If you want 100, you have to do this f-cost check that will make all the default tests path with optimal paths. Okay? So you'll get a 98 if you don't do that, but the rest of it shouldn't be that bad. You're basically just like in assignment 1, actually I'll show that in the code when I get to it. Here's an excellent paper on the current state-of-the-art in bidirectional search. Links to a lot of the theory of bidirectional search, and you will see if you read this why it's so hard to talk about and why I'm not getting into that theory in this class, because this is not a search course, believe it or not. It's just a part of the course. This will not be tested for the exam, but if you're interested in bidirectional search, it's the best research, or the best paper out there right now. And if you want a different demo of bidirectional search, there's another one here, which is not my particular demo. Okay, so now we will go into the code of the assignment. And just like before, we have a marks file, we have the GUI, I have this binary heap. I won't go into how that works. You can just use it if you want to. We have environment, that's identical, index, identical, obfuscated solution code. That's not identical, but it's the same thing. You don't get to look at it. I won't click on that one. And here is your code. So let's go through this real quick. I have included a recommended order that I recommend completing the assignment in. Because this assignment is like building a house. You can't build the roof first. Okay, there's lots of stuff that has to happen before you build the roof. So I recommend first construct the function which computes whether an agent of a given size can fit in a given XY location. Okay? And then that will be used for your BFS for your connected sector computation. So that function is down here. If we scroll down, there is a canFit function, canFit XY size. Returns true if all the squares from that XY out and down from the size are all the same color. Okay? Next, once you've done that, complete the compute sectors algorithm using the 4-directional BFS shown in the class slides. So you can see here that in the constructor of the object, the compute sectors function is called for you already. So you never need to call that because it's called when it's done or when it's constructed. And then here is the compute sectors function. Okay? So all your code will just there. You'll set up a 3-dimensional array, x, y, size, and then go from there. What I do recommend, however, is get the whole assignment working with size 1. If you're not familiar with 3D arrays and you're not super comfortable with that, you can still pass the assignment. If you don't do size 2 and 3, you'll just lose like 30 marks or something. So if you want to, you can just do size 1 first, get it all working, and then go back and add the size loop into all this computation. So do it all for size 1, then go back if you're not super comfortable with that. So then, use the result of step 2 to complete the isConnected function, and then test it with the UI. So there's an isConnected function, right? So right now, in Search Student, what I have is that I'm saying they are connected if they're the same color, which is not correct, right? So by default, look, all the blue ones are being highlighted. All the green ones are being highlighted. But of course, these green ones aren't actually these. So if I look at the solution, these green ones are connected, but not connected to the other ones. So this default function I give you, instead of checking your sectors map, it's just checking the environment. So you have to change that, of course. Next, do the isLegalAction function. That will be used by your search iteration. And so the isLegalAction function, if I come down here, isLegalAction, this is from assignment 1, so I have to delete that. I will put in a new comment here when I get back before I release it. This is where you'll do that optimization, where instead of doing all the checks for all the different things, you're just looking at the computed sectors that you already have done. So in here, you're checking the computed sectors. So now that you have legal actions, complete the start search function. And so the start search function is here. It takes in an extra parameter this time called size, because the GUI has a particular size in it. And so you set the size here. So wherever you are concerned about passing size around in your assignment, it's the this.size variable. That's it. And in here, you'll create the open and close list. And just remember, if, now you have up here, this.config. This actually has another thing, config.bidirectional. And this is going to be whether bidirectional or not. So if config.bidirectional is true, you're doing bidirectional search. If it's false, you're doing unidirectional search. And so if that's true, you need to make 2 open lists and 2 closed lists in the start search function. Next, you have get open and get closed. I don't need to go down there. You know what they are. Just return all the things in the open and the closed list. And just realize that if you are using the binary heap, inside the binary heap, there's an array called content that content array is the thing that you'll iterate over to get all the nodes to put into the open list. So you just be aware of how that binary heap structure actually works. And if you are bidirectional, add the contents of both open lists and both closed lists so the visualization can see both of them. Next, complete search iteration using A star with a heuristic of 0. Now that you've done all the hard stuff, you can do the easy thing, which is the actual algorithm, right? Because A star should be about 5 lines of code at this point. It's literally a copy and paste of assignment 1, but it's get min f instead of shift or pop. That's it. Then you can test your A star with a 0 heuristic. So if I come to the solution and I come down here and set no heuristic, A star with no heuristic is optimal. So I should be able to hit run tests here and all the tests will pass. Okay? All the tests will pass. And that's because I have a 0 heuristic. Now, if I hit 8 directional, it should also pass, but it should be faster because now I'm using a heuristic, right? So before you do your heuristic, test to see if your A star is working with the 0 heuristic. If it isn't, then there's a problem with your algorithm. If it is working with a 0 heuristic, but not with your heuristic, you know the problem is with your heuristic. So that's a way that you can debug that. Next, make sure all the tests pass, because that's what you're going to be tested on. And then, for 6980, implement bidirectional search. How do you do that? Well, just like assignment 1, inside your search iteration, I have if this.config.bidirectional, I call the other search algorithm, right? So here is where you would do your A star search, and down here is where you would do your bidirectional search, okay? So down here, it's a little bit annoying. It is a little bit annoying. And I see some grumpy faces out there, but it's not that bad. And I think once you get it to work, it's like the first time I got bidirectional search working, it's like, I don't know, maybe I'm a nerd like this, but think of what we did as human beings. We took lightning and put it into rocks, and now the lightning in the rocks can tell us where to go. Do you understand how mind-blowing that is? Like, we take, this is rocks, it's minerals, it's like silicon, right? And then we take electricity, and that combination can do something. And the first time I got A star search to work on my own and bidirectional search, I was like, I don't know, it's like it's alive almost. It's a thing that I wrote that can help me. It's crazy. Anyway, that's how I view it anyway. So I think I'm lucky to get to teach this because I really like it. But I think you'll really learn something from this assignment. And nobody who has finished the course in the past has ever regretted doing assignment number 2, right? They all think that it's a good assignment. Yes, it's a lot of work, but I really did learn something. And then the other assignments are probably like half the amount of actual coding of assignment 2. So let me just double check. I don't think I have anything else left in here. I'll just scroll through it. Is connected, we did that. Is legal action, did that. Compute sectors, did that. Is legal action, search iteration. I guess I could just show you real quick an example of if I go to blank. I was talking last night in preparation for this lecture to the author of that paper that I just linked, who is like one of the 3 world experts on bidirectional search. And I said, okay, this is the easy way I'm going to tell them how to make bidirectional A star optimal, is by looking at the F value and seeing if it's bigger than my current best path. And he said, yes, that is the easiest way, but in practice, in grid worlds, with a good heuristic, it will not save you any node expansions. So the whole point of doing it is kind of lost, because in this particular environment that we're using, it won't actually help us. It will only help us to learn. But here's what it looks like. Solution A star, bidirectional. Now, watch this. If I set this to 8-directional heuristic, and I click over here, and I click over here, oh, wow. It only took from 1 open list. Why? That's actually not an error. It's because all the F costs are the same, because there's no obstacles. If there's no obstacles, then the 8-directional Manhattan distance tells us the actual value. So it's just guiding us right towards in the worst case, right? But watch, if I set this to the 0 heuristic, then I actually will see this. Because the 0 heuristic is taking the minimum G value, which looks at both open lists and takes the thing that's closest to its respective starting position. Now just watch. When the two circles meet, it will find a solution and draw it, but I'm not sure yet that it's the minimal solution, so the search will keep going. If you stop your bidirectional search at that point where you make the first connection, you'll get a 98. Okay? The tests passing and the keeping going to make sure that it's the optimal path, that's the last 2% of the assignment. So you don't have to do that if you don't want to do have to do that extra check. But you can see how much extra work is being done to ensure that that's the optimal path. And in reality, the really efficient, good way of doing this involves taking the things that are close. It's this weird data structure. It's all explained in the paper, but there's a good reason I'm not getting you to do it. Okay? So for our assignment, for our particular use case, let me just show you another one just to show you that I'm not lying. If I go to like dense caves, or let's say sparse caves, it's better. Sparse caves, grid off, instant path, unidirectional. If I go from here down to here, no, I want the A star. So you can see how much A star saves us, right? Ideally, bidirectional search would help us here, but in practice, because our heuristic is really good, it actually hurts us. Okay? It doesn't give us a suboptimal path, but we do have to search more to ensure that the path that we found was optimal. So just keep that in mind. In our particular use case, it's not really helping us. It's just helping us to learn and implement this cool algorithm, at least the one that I think. Oh, very, very, very last thing. I got 2 minutes left to fit it in the video, is the marking file, which of course is very important. So we got our 5% for that style, 5% for using functions properly. Is legal action function, that needs to be correct. A star pathfinding, here's the tests we are going to do. We are going to do 8-directional heuristic with 8-directional movement, 4-directional heuristic with 4-directional movement, and 0 heuristic with 8-directional movement. Your tests have to pass for all of those. Why aren't we doing it with 4-directional heuristic and 8-directional movement? Because it's not an admissible heuristic. So your paths won't be optimal, so we're not doing a suboptimal testing. Has to interact properly, et cetera, et cetera. A-star pathfinding for objects of size 2 and 3, that's worth 15%. Same thing, we're just going to set the size different. Connectedness, that's 15%. For sizes 2 and 3, that's another 5%. And then bidirectional search with without optimality is 18%. With optimality is the total, is the last 2%. Any questions? I know it seems like an insane amount of stuff, but really, the connectedness part, that's like writing that loop, that like loop with 4 nested things. It's like a 3D loop with a BFS in the middle. That's the hardest part about